Good morning, everyone. So, welcome back to week 8 session. So, today we will be going through the week 8 lecture material. And like the last time, we will be solving the week 8 problems from the last year. So, in between, if you have any question, any doubts, do let me know. And I hope you enjoy this today's session. So, in the week 8, I hope everyone have went through the lecture materials. Okay. So the main topic which was covered during this week was mainly about the training strategies. Okay, training a deep neural network is kind of a not that much easy task as you come across a lot of difficulties. So the difficulties is basically, so I will be just this week lecture was basically based upon how to train a proper model. Okay, so the first thing we'll be recapping some of the content which I will be going through for this session was recap of neural network training neural network. Okay. Then we'll be talking about, as of now, we were just saying about the supervised learning. Okay. So on a broad level, deep learning can be classified into three tasks: supervised, unsupervised, and reinforcement learning. Okay. All the tasks which people are working in either belongs to some of this domain. Okay. So we seeing today one of the new kind of a task, that is the unsupervised task. Okay. Then we will be talking about some of the strategies which are used in the latest chat GPT kind of a model so that the training is stable. So what do I mean by stable training? Okay. So training a deep neural network means directly having a lot of layers and like that. It's it doesn't work out actually because you can just go and this data set is available on PyTorch. So you can just write some of the layers and just see and give a constant learning rate and all. Okay. It's not easy at all. Okay. So there is a lot of strategies which from 2010 onwards people have developed so that we can train a proper stable model with time. Okay. So whatever you are looking for the this week content, it has been accumulated for last 20, 30 decades, what researchers have tried to came up with. Okay. Next is better activation function. Better initialization strategies. So I will be just clarifying that what is all meant. And lastly, we will be talking about some new concept, I guess, because you might be aware of the normal deep neural network training. You are aware of activation function, that is a non-linearity I'm talking about. Better initialization, so it's by the namesake how to initialize the model basically. But batch normalization is a new concept, kind of. So there is a variant of batch normalization. Okay, there is a batch normalization, real normalization, group normalization, and all. Okay. So, but for the weak content, actually, we'll be just going to the batch normalization. Okay. So how this all techniques make the training smooth. Okay. And like that, we'll be just solving problem solving for the last year assignment problems. Okay. Okay. So firstly, let's go through that. First of all, I will just give you a glance of what is meant by the stable training. Okay. So as you all know that we have our model, which is a black box model basically, and it's very large because you We don't know basically. As of now, it's still a hot topic of research that how the model is learning basically. Okay. So usually people assume that it's a black box model where we want to have an interpretation. Okay. We give input that is X, we get some output that is Y. Okay. And this is a models. A model is having some parameter theta. Okay. And also we for each corresponding X, we have it's give a prediction. We have a original labels, original kind of output. Okay. Then we calculate a loss. Okay. The loss can be cross entropy, MSC, any kind of a loss. Okay. Then we backpropagate it using backpropagation. So backpropagation is just kind of a chain rule basically. Okay, when we have a multiple functions, how to take a derivative of function of a function like that. So chain rule basically. So it's just made up on the chain rule formulation. And what it does is that it just update the parameter on some gradient. So that is what is happening actually. Okay. So we update the parameter and we want this loss to be minimum. Minimum in the sense because that's what we want to know. Basically, if you are doing a regression, we want to fit a kind of a curve which minimizes our means kind of a task we are doing. If it's classification, we want to correctly classify all the points. If it is a regression, we want to correctly output to the correct value of this regressive value, basically. Okay. So this is how all the model looks like. Okay. In deep learning, this model is just by the neural network, takes the input, predicts the output, predicted output. Then we have original output. We have certain loss which we want to minimize it. We backpropagate it, update the parameter. And that is what is happening actually in the chat GPT or any kind of a model. Okay. So you give a sentence, ask some question, it just passes to the model and it generates the sequence basically. So it's a just sequence to sequence model basically. Okay. So this kind of a task is basically is called as a supervised task. Supervised task in the sense we already have the access to the labels. Okay, we have some objective in the form of loss objective which we want to minimize it. Okay, and that drives the whole optimization of parameters. Okay, so we already have access to the labels, so that is the supervised. Now you can assume that what will be the unsupervised learning. So in unsupervised learning, we don't know why. We don't have access to why. It's kind of way like that. Suppose I have a class distribution. Okay, means class is there and not class. Um, okay, normal clustering problem we'll be taking it. Okay, so suppose I have a data points. Okay, so this is some random data point features I'm plotting it. Okay, now I don't know about anything about this data set. That what this data set means, what's the output basically. Okay, in the classification we know which class it belongs. In the regression we know that for the corresponding value of X, what's the output. Okay, here we have been given some data. We need to have some interpretation of data. For example, in this data, if you see, we have a two clusters. Okay, it is visible, so that's why it's easy. We know that there is a two clusters. Then we can ask that how to divide this data point into two clusters and all. So that is kind of an unsupervised task. It can be three clusters, as many clusters, but we don't know. We want to find the optimal number of clusters which are present in the data set. So that can convey some meaning because there is a lot of data available. If you go to bank, we have a data set, defaulter, non-defaulters, how whom to give a loan. They have a credit score and all. Okay, so they make a cluster that how to means a certain customer is coming. Okay, we be having a certain feature that what's the age, what's the gender, what how is means how much he's earning. Okay, how much property he's having, whether he can able to repay the loans or not. Okay, so that's how we want to have a cluster that if it belongs to certain cluster, how we can have certain kind of a task. Okay. Now there is another kind of ML is which is reinforcement learning. So in reinforcement learning, it's kind of a means we need to learn the rules basically. So for example, uh, rules in the form of, for example, you can think it of as you play a game. Okay, we have certain chess game is there. Okay, okay, we have a chessboard. Then there is a black and white we are having. Okay, then if we are given certain position of on the board, okay, we want to know that what's the best possible strategy for black. If he if the chance of playing is for the black, if it's for the white, what's the possible best move for the white? Okay, so here we try to model this thing in the form of rewards. So it's like, for example, if it gives of the best position, maybe giving a most reward. If it's giving a bad result, we end up in losing. It's a negative reward kind of way. So this reward we try to optimize it in a long term. It's kind of a you are in an unknown territory. Okay. Now doing certain action, you get some reward. That is a positive reward. And if you do action which is not with respect to the environment, then you get a negative reward. So common example is kind of a when you are childhood, okay, in during a childhood. So whenever you do some mistake, so your father or mother, you might have got some slap on a face, something like that. Okay. So that act as a signal that child get to know that I don't need to do this. If I broke my toy or something like that, I'm gonna get a beat from a father and mother. So that kind of a thing we try to model here. So if we have our agent in certain environment, we want to give reward which tells us that yeah, this action was good. So we want to learn which action to take basically. So here we ask the question that what action to take given we are in certain state. Okay. So that is was the reinforcement. And these three are the classification, broad classification of a deep learning. Okay. So major of the means kind of a what research mainly is focused now is on unsupervised in RL, self-supervised kind of a task. Supervised kind of a task are available, but it's kind of a means kind of a done in the research community. So everything is now moving towards unsupervised RL, optimal control is there, self-supervised. So a lot of different domain which is getting opened. Okay. So I hope you got the whole point that how this whole pipeline of a ML model is. Okay. Now training this model is not kind of a simple task. Okay, this optimization, it looks simple, okay, mathematically, but we are working on a computer and we are working with certain, for example, you know that in the any programming language, okay, we are having a certain float, int, characters, strings like that, okay, data types. Now the float is stored in 16-bit precision, okay, so 16 bits basically. Now the thing is, this works in a continuum basically. This does not work in the case of discretized version. So you end up with a lot of error and all which get accumulated with time, and it's kind of a not easy simple task basically, simple one. And basically what we want is if we have a loss here and if we have a number of epochs or iterations, okay, we want our idle loss to go down with time. That's what we want. If it's running, the optimization should go, but it does not. Sometimes it's kind of a fluctuate, sometimes it's oscillates. Okay. Sometimes you'll be getting like this, sometimes it diverges as well. Okay, there's a lot of possibilities which happen. So stable training is that basically we want it to be minimum. Okay, we want to minimize the this thing. So we want our training curve to look something like this. So that is what meant by stable training. So that at every epoch or iteration, our objective is getting decreased. Okay, so that's what we want. Okay, we don't want it to be something like oscillate something. We don't want like that. So that's kind of unstable training. Okay, so the strategies which we'll be running this week is basically about the stable training. Okay, so that's what was covered in the batch normalization, activation function and all. So let's have some recap, okay, of the training thing. So basically, you know that if we have been given any model, okay, how we optimize the parameters was based on this equation, theta t minus 1, okay, minus eta, which was the step size. Okay, and it depends upon what kind of a Adam RMS prop or what we have studied already about optimizer. Then it was a derivative of our loss function with respect to at theta t minus 1. So this is what every kind of a model was trying to do in the end. Okay. So the thing is, sometimes the gradient, this value, the purpose for having this eta t, as if you remember, was basically so that our gradient does not blow up. Okay, what is meant by the blow up? Suppose this is kind of a contour plot of our objective function which we want to minimize. Okay, and we are at this particular point. And suppose we took a direction to minimize and it gave us, and we eta and del, it's just pushing at this direction. So it's kind of a, we wanted, the ideal direction was this basically. We want to move in the ideal direction, but the thing is, we don't know the ideal direction. And taking eta t and the gradient, we might end up going somewhere else, unknown region and all. Okay. So that is why we sometimes see a curve. If you have taken any ML model, some spiking curve we'll be seeing with time. So it happens. Okay. So the thing is, and also if you take eta is was large, if eta is so small, we'll be taking small step. It will be taking a lot of time. That also we don't want. Okay. So what we want is basically we want to go in an optimal rate to the minima without much oscillations and all. So that's the kind of a objective we want. Okay. So this to we need to balance this thing. So you might have seen that RMS prop, Adam. So that was the strategy they were using for the making this optimization procedure much more smoother. Okay. So what this basically del theta L is basically dou L by dou theta. Then we know that L is a function of real, because basically the what are how the neural network looks like basically. We have input real, we have output real, means hidden reals, and we have certain output reals. Okay, each input real will be having certain hidden real, might be having certain number of neurons. Then we were adding non-linearity upon that, and we were getting the output. So it's kind of a matrix multiplication, adding bias, taking non-linearity. It's just a simple thing. Okay, by the matrix multiplication, either we are rotating, stretching, squeezing. Okay, so basically, if you want to see the interpretation of for this is basically, so suppose we are at this point, when we multiply, when the number of hidden layer and the input layer are the same. So by multiplication, matrix multiplication, we end up in certain region, we move towards other point. So that's what the matrix multiplication does actually. Okay, it just create a grade, means flow particle, it is moving basically kind of it. Okay, and then bias is there, so bias will add up and it will be getting us somewhere else. Okay, and again this non-linearity, it will just project us somewhere back. So ideally we are going in certain direction. Okay, and the main purpose for adding this bias was basically so that if we are not near the origin Suppose our cluster is here. So if we don't add a bias, we never reach here, the decision boundary. It won't it won't never reach here. So that's why we add a bias. Non-linearity we add because what will happen if you don't have a non-linearity? Then you output matlab hidden representation at any real L. It will be just W times W1 times X input. I am for simplicity, I'm trying to avoid the bias term here. Okay. Then again, matrix multiplication is WL minus 1. Okay. So if you see here, we are just multiplying a lot of matrices. That's it. Nothing else we are doing it. You can replace it with a capital matrix and H. So it will again remain a linear. If you don't add a non-linearity, it remains the linear. So the purpose of non-linearity is basically to run a non-linear decision boundaries, non-linear functions, and all. Otherwise, the deep learning won't work out. Okay. So you can either go and just check it out. Means PyTorch basically go and construct a PyTorch, don't activation in between the layers and just see it. Your accuracy won't improve with time. It will just try to find it and it will oscillate. Then you'll be realize that your objective will oscillate. That's it. Nothing else it will be doing. But if when will you add this non-linearity, then you can see a kind of a smooth training kind of a thing. Okay. So that's kind of an exercise. Whatever we are learning, it's much more advised that you just code it up and see it as well. Because it will be helping you conceptualize whatever you are learning it. And the basic framework is just PyTorch. You don't need to write this whole gradient and all yourself. Okay. So the normal is just loss dot backward. If you do in PyTorch, it will automatically calculate the gradient for you. So it's much more easier there actually. Okay. So you are learning just for the black box how it looks like. So that's all you are learning. But it's advisable so that you just go and just check out that how it works practically as well. So there are tons of data set you can try. MNIST is there. Okay, CFAR is there, CFAR 10. Okay, some regression task you can pick it up on from the Kaggle. Okay. And using PyTorch, just build some model. Okay, and just see whatever the theory you have learned in practical, taking more, taking a learning rate very large, taking a learning rate very small. Okay, having a model with more layers, less layers, more number of hidden neurons, different activation functions. Okay, so that's the main purpose. Just I won't advise just go through this material because in the end you are not visualizing what is happening. Okay, so the main purpose for this course is just kind of give you a background maturity that what's how the building blocks looks like for a deep learning. Okay, but it's very much advisable. See the experimental part as well. You need to experiment with different AI, and then only you can able to just check it out. Okay. So the thing you are seeing the neural network, the backpropagation, the learning algorithm in the end we are having is the backpropagation. We are having a set of parameters which we don't want to run, and deep learning it's just kind of optimizing the parameters and just try to run the function. Okay. And the learning before it wasn't that much great before 2006 and 10. If you see when there weren't any GPUs and all, okay. So people were means writing a manually this training loop and all, okay. It was so boredom kind of a task. But now you have everything, the all the frameworks are there. Just go and check it out, okay. And also the training before it, people means training wasn't that much great. Okay, as I mentioned, it was always diverging. It wasn't converging with time. Theoretically, it should converge, but it was not working. Okay, so the thing between deep learning is that deep learning is why I'm telling you to experiment is that theoretically you will be getting something, but practically it does not work out. That's happened most of the time in deep learning. And practically something work out, you don't have any theory. Okay, so both the things happens. So that's why whatever you're learning, that just try to see whether it's kind of a working or not. So now we'll be looking one kind of a task that what people were doing before, okay, to train a very deep neural network kind of an architecture. Okay, so first of all, see one kind of an unsupervised task, and we have already seen this kind of a task in the parallel weeks as well. So you might be remember that we see denoising autoencoder. So where we passed an image, add some noise, and ask the model to remove the noise. Okay, so it was like that. We add x, x was there. We corrupt it with some noise epsilon. Epsilon was coming from the Gaussian distribution, and then we asked the model to predict x. Okay, it was a parameter theta, and it takes input x epsilon. And we want to minimize, this is the x predict, and we want to minimize x minus x constructed. So this was kind of a reconstruction thing we were doing it. So this was the objective we were doing in the denoising autoencoder. We were adding something noise, and after passing to the model, the noisy version of the data, it will we wanted to construct back the data, and then that was the task we were doing at that time. Okay, and it's kind of a denoising because we don't have any labels here. So it's just simple thing. Eh, Denoising, just add noise to your data, ask the model to predict the correct data. So whenever the noisy data is coming, you can get a pure data out of it, basically. Pure, okay. So that's the objective. So it's kind of a, this was kind the construction loss. And this kind of loss is very much popular in the unsupervised learning task. So in the unsupervised learning task, people we have a data. So for example, we have an images there. Okay, we be just taking certain region and we be removing that region basically. And we be asking our model to predict that particular region, given this whole information basically. So that's a very quite powerful thing. Okay, so you might have seen a lot of time whenever you give a man without a face something to a for a multi-modal chat GPT 4, okay, it will just reconstruct back something. So that is how it works. Okay, so so this was the normal reconstruction loss which we are having. Okay, and the model, for example, as I mentioned, it looks something like this. After each layer, we have non-linearity. This is our input. This is our output y capped, y predicted. These are the number of neurons we are having at each layer. Okay, and we have a lot of layers basically, total L number of layers and 1 and 2. And there is a weight connection here basically, which I'm not showing. Okay, so if the thing was, suppose instead of x cap, y cap means the prediction, I can predict the x, what we were doing in the normal or denoising autoencoder. Okay, and our objective was to minimize this objective, which I wrote on the top here. Okay, minimize over the value theta such that this is a function of theta because x is given, x cap is a function of theta, and noise is a deterministic quantity which we are adding it. Okay. So initially, what people were means doing, because training this whole kind of an architecture is not easy as it seems to be. So first of all, we can freeze this all layer. Okay, if these parameters are fixed. Okay, then we know that it's just a function of this weights, this W1 weights. Okay. So now our problem become easier. Okay. Because the gradient, whatever we'll be taking, because this function get deterministic, and a derivative with respect to some deterministic thing gets to be zero. Okay. So the optimization with with respect to learning these weights and bias. Okay. And we know the objective which we want to minimize it. Okay. So once this model is will be this weight will be getting, we'll be minimizing this weight. Then we'll be freezing means rest of the architecture, keeping L2 learnable. So like this, people were training the very large language means very large models before 2010 and all. It was working, but not to a great extent at that time. But now we have a GPUs. So why the GPUs is getting used is basically in the end what we are doing. Add multiplying by the weights, adding bias, then non-linearity, again weight multiplication, adding bias. So this sequence of operation which is happening. So GPUs in the gaming, it's very much popular. The ending of any gaming thing. Okay, you can't play any game. Okay, without GPUs thing. Okay, so GPUs are very faster for the matrix multiplication. So one kind of operation which we want to do again and again, GPU you should use. Okay, so GPU you have a CUDA. Okay, where you train the model and it's very faster there. You have CPU as well. The CPU is used. It's kind of a sequential decision. Okay, where the next you want to do something. For example, you have a sequence which you want to execute on a system. Okay, and that sequence is not kind of a, for example, here we have a weight. Weight can be made parallelizable using a GPUs. Okay, in the CPU, if one kind of if my operation are very much sequential, then this CPU is used. If we want to do the same operation again and again, GPU is used. Okay. And as I mentioned, means this training kind of worked out previously, that freezing one layer, training rest of the weights and all. So actually, what's the problem there is actually, if you see, the problem is that we have a weight which belongs to very high dimension. D is very much larger than one. Okay. So any deep learning architecture, the weights it's just normal the elements of the matrices biases. This is what you learn in the deep learning thing in order to minimize the objective. Okay. Now the thing is the loss curvature, the contour plot, it's much more easier to visualize in 2D. But in 2D also it's not easy basically. But as we have more and more parameter, our objective lies in a very high dimension. And it's non-convex as well. So what do I mean by non-convex? So convexity is defined as if certain function is there. If I have if I take 2 points, any 2 points, and all my function value between these 2 point rise or equivalent to this thing, that is a convex function. I take 2 points, join the 2 points, and all the function value rise below that this particular line. This is a convex function. Okay, for any 2 point. So what do I mean by that? For all x comma y belongs to the domain D, any z which is a combination of which is in between x and y basically. So linear combination. F of z is strictly less than theta f of x plus 1 minus theta f of y. So this is what the mathematical definition of convex function is about. Okay. So theta lies between 0 to 1. Okay. Non-convex function is something like this. Why it's the non-convex? You can see that if I take just 2 points, my function value is up. So I hope you are getting visual. introduce that what's the non-convex functions are. So in the higher dimension, we have a very highly non-convex functions. So our objective L is basically highly non-convex function in higher dimension. Okay. And the thing is about in the non-convex setting is that in the convex, if I start my optimization, there is a chance I will be reaching here actually because we have a one minima. That is a local minimum, global minima as well. In the non-convex setting, we have a multiple minimas. One minima is here, and finding the global minima is kind of a task, and it's still an open problem. Global optima in non-convex function. It's kind of a research problem, okay, and it's not easy, okay, until unless you don't have a very tactable because we don't have a tactable form of the function. If you know the form of a function, you can find the global whatever you were doing. Differentiate is set to zero, then you were trying to find out all the minima and just see which one give you the least one. Okay, but here in the deep learning, it's not easy at all. Okay, although we want global minima, but we are happy if we can able to reach the local minima as well. Okay, so that's what the optimization should does. We want to reach to the near local minima in a highly non-convex landscape. Okay. So if you remember, we were talking about different strategies last week, I guess. Okay, so the strategies we were talking about was training, testing error. We were doing kind of a data augmentation, okay, adding noise, regularization, and all stuff we were doing. Okay. But the thing is, why we want to do that all thing? Okay. Why does regularization helps? So last week also I gave you the intuition that how it helps. So if you have 2D contours, okay, now you add L1, you add something weight in the L1 norm. L1 norm wall is basically looks something like this. And this L1 norm wall, what it does is it does tell your weights to be zero sparse basically. And L2 ball have L2 norm is having a circular. So it does not want you to go far apart. Then we talked about where this both of them met. That was the point we wanted. We don't want to be very far apart as well. We want to remain the close so that it does not underfit, overfit. This whole thing we talked about. Okay. So with time, a lot of different thing happened. Okay, about this deep neural network and better optimization techniques. And which we already have seen. So Adam. So most commonly optimizer which is used is Adam. Okay. So it works in any highly non-convex setting as well. Okay. So whenever you are writing a code, if you don't know which optimizer to use, Adam is the best one to go through it. Okay. That is why with my experience. Okay. Now better regularization technique we talked about. Adding certain loss function we added, perturb the input, data augment the input. This all thing we did it. These two things we have already did it. And our model is performing quite well with these auto techniques. Today we will be talking about better activation in the better activation, that is sigma non-linearity function, and better weight initialization. Okay. So basically, why we need better activation and better weight initialization. So weight means I'm talking about the weight of our model. Okay. So about better weights, we were talking about the weights initialization. So weight initialization, initially we need to assume some certain weights, then only we can optimize our weights basically. Okay. And activation function. So we had a gradient. Then all the problems comes when certain gradient vanishes and your model still is not performing good enough. Gradient helps model to run. If our gradient is kind of a dead, model won't run anything at all. Okay. So let's see about this activation functions. So activation function, as I mentioned, it's just about running highly means non-linear functions basically. Okay. Otherwise, if you don't have a non-linearity function, then it's kind of a hard. Okay. And one kind of activation which I will talk about is sigmoid. So it was covered in the week lectures. So sigmoid function is something like this. Okay. It's not proper. Okay. Just something. Let me redraw it. Something like this. Okay. It's not proper. Okay. So basically, the thing is, it's between 0 to 1. That's one thing. The second thing is it's continuous. It's kind of a continuously differentiable and continuous. But the thing is, if we have for very up after certain region, okay, my kind of a slope is constant. If slope is constant, the gradient vanishes. We don't have a proper information. If I am here, I am at this point. If I take a derivative of a point, it's not giving me enough gradient for my model to run. Okay. So basically what we wanted is that the gradient it should be zero only whenever the model has came up to the local optima. But if I grade because of our activation, it should be a local optima with respect to the weights, not with respect to the activations. Okay. So if our activation is not only giving a proper signal for a model to descend, okay, then it's kind of a not running. It's stagnant. You might be saying something like this. It's kind of like this, but we wanted something like closer to it should with time it should go to 0. That's what we want. Okay, and also the thing is the sigmoid will always the gradient is positive. Okay, so it will never give us the negative gradient at all because this does not have a negative gradient. Okay, so that's why the new kind of an means activation people came up with. So one other activation is just it's sibling kind of a activation. I don't call it as a means new activation, that is 10H. Okay, just you take this part, make it between -1 to 1. It's remain the same. And the thing is about is that it having a both positive negative thing means the value of activation is both positive and negative. And it also saturate. Okay, so that's the same reason. So both of them is you can just convert sigmoid to 10H, 10H to sigmoid. Okay, there is a clear relation between sigmoid with something like 1 plus e to the power minus 6 10h looks something like e to the power x minus e to the power minus x divided by e to the power x plus e to the power minus x, something like this. Okay. So both of them you can just convert, take e to the power x, substitute there in the 10h. You can get some relation between 10h function and the sigmoid function. Okay. So now the thing was all our gradient was between means the activation was between 0 to 1. It's kind of a restricting us. Means restricting in the sense the output we be getting the 0 to 1. But there is a point that at a certain point we wanted kind of a more value than 0 to 1. That's it. Okay. So that's why then what an new kind of an activation came. Okay. So that's radio function. So the thing about radio function is that it's also non-linear. It's piecewise continuous. It's not differentiable at this point. Okay. It's kind of a f of x. You can write it as max of 0 comma x. Okay. And the gradient of this function, if you write it as the activation function, it will be 1 if x is greater than or equal to 0 or 0 otherwise. Okay. But it's not differentiable actually. This I wrote x greater than or equal to 0, but it should be a strict x greater than 0. Okay, it's continuous and it's also kind of a the derivative exists and we don't have a lot of computation in as unlike sigmoid and the 10h where we need to do some certain computation to calculate the gradient and all. Here the gradient form is very easy. So computationally people prefer the ReLU functions. Okay. So and the thing was it gives us more value as well. Okay, it does not restrict the output to be just between 0 to 1 and all. Okay, and the proper value. But the thing was, if my value is negative, then our output is always 0. It won't. There isn't a signal at all. Okay, so this area we don't have a signal at all. The gradient is vanishes. Okay, so that's why the some new combination was which was suggested. We added certain kind of a function which was covered as a GERU and all. Okay. So that was also covered in the so leaky yellow. We had a one more state and so just remember we should have an activation function which should be continuous, differentiable, it should be fast, and it should be non-linear, and it should not be basically the gradient should not saturate and it should not squeeze the value between 0 and 1, something like that. So that kind of an activation works properly. That was seen in basically in the practical. Experimental activation should be bounded. Okay, so before 2010, people were just using sigmoid and 10h kind of an activation. But with time, they thought that no, this radio came into the picture and it just changed everything. So the theory, that's why it told you. The theory, it just told that it should be bounded. Bounded in the sense maximum and minimum should be existing. But for the radio, we don't have, it's not bounded, it's infinity. 0 to infinity, basically. Okay. So that was the better activation functions. Okay. So sigmoid and kind of the new function is just used basically in the CNN and all. Okay. Now coming to the weight initialization, which was covered. Okay. So for example, if we initialize all the models weights to 0, then what happens is that at initial level, okay, all my weights are 0. So the only the bias will be there, and the bias is kind of the same. Bias is also 0. So my all my nuance is having a same value. And when you take a gradient, everyone will be means updating in the same manner. Okay. So that's why we add basically we just the theta we just sample from a Gaussian distribution with mean 0 and I. Okay, with certain kind of normalization constant z and all. Okay. So that is what was covered in this week. Okay, better initialization techniques and all. Okay. And if we are not went through the lecture material, it's just like we just go through the lecture material again in once. So just properly just go know that how why we use this thing. Okay. The next thing is batch normalization. So deep learning model actually one thing is that it just prefer all my input to be coming from the Gaussian. Okay. So in the batch normalization, after each layer, we just take a mean or across because we are working in the batch, mini batch gradient descent we talk about. We take a mean of that vector across that particular batch, subtract it, take a standard deviation. So we again get normal standard kind of a means normal distribution, and it ensures that there is a smooth functioning. Otherwise, if my certain bits get exploded, okay, then the learning becomes difficult. Basically, you want to play with the model within this normal ball between -1 to 1. So that's the main thing. Okay. So that is the main batch normalization, you know. So let's come to talk about the last year assignment problems. Okay. So I hope I have recapped the stuff what was needed. Okay. And again, if something is needed, I will just recapping it. Okay. Okay. So the first problem is choose the incorrect statement with respect to unsupervised pre-training. Autoencoder can be used to run the presentation from the input. So yeah, autoencoder, we just reconstruct back and run the representation. That is correct. We need to choose incorrect. We converge faster to a minima using unsupervised pre-training. Yes. So if you are low weights, you have initialized in such a way that it's pre-trained and just to fine tune on it, it just converge. Okay. Hidden layers used in the feed forward neural network are initialized with random weights. No. In unsupervised pre-training, weights and while pre-training is used for the initialization for the feed forward neural network. Okay. So the option is C. Option is C. So the question was in the unsupervised pre-training. Okay, which statement is wrong? So if you remember in the unsupervised training, we just reconstruct back our output and the weights we have, the same weight we used to initialize to perform certain tasks. Okay. Now the second question, we have observed that a sigmoid neuron has become saturated. Okay, the saturated. So it's just telling that saturated means after a certain time it's just becoming 0 or 1. Okay. What might be the value of output at this neuron? Output. So the option is 0.94, 0.04, 0.65, 0.35. So it become dead when it is very much closer to the 0 or very much closer to the 1. So the is just 0.94. Okay, when it's just 0.94 or 0.04. So the option is two of them is correct. 0.94 and 0.04. That's why it's becoming saturated. We don't have enough gradient to flow backward to make our model run. Okay. We want to do the gradient descent. The only thing is that the way the non-linearity, we don't want it to make our learning worse. Okay. Now suppose we have a neural network. network. Okay, certain neural network is given. So the neural network looks something like this. We have a three input, two hidden at first, second hidden, and this is the output. This is our output here. This is hidden 1, 2, H11, H21. And this is the input X1, H2, X3. If the edges from hidden layer 1 to hidden layer 2 have weights W1 and W2, this is we are talking about this W1 and W2. Which of the following are possible values of gradient of del of W1 and del of W2, given that sigmoid is used as an activation function? Okay, so we have been given sigmoid. That's one thing. And they are asking about the gradient of W1 and the gradient of W2. Okay. And the normal the derivative. So basically, we know that we need to take a derivative of a loss. Okay. With respect to suppose this is the W3. Okay. With respect to W3, then W3 with respect to our activation sigma, then our activation with the initial hidden representation delta H, and that delta H will be giving us the gradient with W1 and W2. And the thing about the sigmoid activation, we are using it. As I mentioned, the sigmoid activation is either it just always positive actually. But the thing is, the gradient means sigmoid activation gradient. If you see it, just Wx sigma 1 of okay sigma f sigma of x 1 minus sigma of x. Okay, and sigma of x is always between 0 to 1. So this quantity always remain the positive. So the gradient of this sigma with respect to W1 and W2 will always either remain positive or negative. So it will either remain this in this quadrant or this quadrant. It won't remain in this second and fourth quadrant. Okay. So the option is 2 comma 2 or minus 1 comma minus 0.1. Okay. So that's the they have given certain coordinates, the gradient. So gradient will either point in this direction or this direction somewhere. Okay. Now, fourth question. Which of the following problems make training a neural network harder while using activation sigmoid activation function? Saturation, that's true. Okay, saturation makes hard. Non-differentiable at 0. It is differentiable. Okay. Computationally expensive, yes, it makes difficult. The range of output is 0 to 1, yes. So the correct answer is A, C, D. Okay. Now, fifth question. What are the problems associated with 10H activation functions? It is not centered at 0. It is centered at 0. Okay. Computationally expensive, yes. You need to compute that expression basically. Saturation, yes. Non-differentiable at 0, it is differentiable at 0. So the option is B and C, computationally expensive and saturation. We have observed the following neural networks with ARU as activation. So again, certain diagram is given. Okay, so this is our input. This is our output. Weights in the first hidden layer and the input layers are not getting updated. First hidden layers and input layer are not getting activated. This thing. Okay, and these two are the bias basically. Choose the correct option of the bias B going to the layer 2. Okay, so if my layer 2 is there, okay, so since weights are not getting activated using the radio activation, then that means I'm below 0. because it's always zero. Okay. And the thing is, if it's remaining below zero, so the thing is the bias, it's kind of a bias is helps to make it positive or negative. Once it becomes negative, the neurons become dead in the radio activation. Because radio is something like this. We are in this region. Okay. Now bias, they are talking about this bias. Okay, the output. If these two layers are not getting updated, that means that there isn't any sufficient flow of gradient to update the weights. Okay. So why this happens is basically if my bias is negative at output, so the gradient at the output with respect to the loss, it will be very much towards the negative, basically. Okay. So that's why it's not getting updated. So the reason is basically with the high negative bias. So if we have a very high, because if it's slow, after updating a weight to there, this might get activated. But if it's a very large bias, it will take a lot of time actually to come up out of it. Okay. So the answer is high negative bias. We trained a fit for a neural network with 10H as an activation function and observe that neurons are getting saturated. So what is the cause of all this phenomena? Weights were initialized to very high values. Yes, we saw it. If my weights are very high initialized, they isn't flow, it gets saturated basically. Okay. Initialized very low, very zero. No, yes, it's also a reason. Weights were initialized to zero. Yes, because at zero also, where the 10H is there, the gradient kind of vanishes. Very small or very large. Okay, the 10H saturated. So the answer is all of this. Eighth question. We trained a feed for a neural network and observe the weights learned are all equal for a single neuron. So you already know the answers. We have initialized all the values to zero, all the values to the equal values. Okay, as we already saw. Okay, question 9. Which of the following is incorrect with respect to batch normalization in neural network? Incorrect. Just remember. We normalize the output produced by each layer before feeding to rest layer. Yes. We divide by the mean across the batch, divide by the variance. Variance and mean are not the neighbor parameter. No, we can make it a neighbor. Okay. So the correct answer is B. And batch normalization lead to better initialization of weights. Yes, it happens. And back propagation can be used with back normalization too. The question 10. Which of the following statement is true with respect to the value function given by a e to the power x minus 1? If x is less than or equal to 0, okay, a e to the power x minus 1. Just let's see how this function looks like. If my x is negative, how this function is. If my x is 0, then it's a minus 1. Minus infinity, then it's kind of in minus 1. So it's something like this kind of a function. Okay. It is discontinuous at 0. No, this function is continuous at 0. Okay. It is non-differentiable at 0. No, it is differentiable at 0. It's the function. It is less computationally expensive than 0. Yes. It is less computationally expensive. Okay. Exponential 0 can have negative values. Yes, minus 1. Okay. If my x is very low, you can keep it. Okay. It's 0 here, and it's kind of an infinity here. The correct answer is basically exponential. You can take a negative value since alpha is 1 here. This a is 1. That is e to the power x minus 1. So e to the power x is getting shifted down, basically. Okay. So it can take a negative, and it is non non-differentiable at zero. Okay. Since alpha at alpha is equal to 1, this function is non-differentiable at 0. Okay. So that's all for guys today for the today's session. And I hope you liked the today's session. So if you have any question, do let me know in the comment box.